and share my screen because I'm getting better at remembering to share. That, and I already forgot to share at the previous lecture, so you guys get a gain from that. On, excuse me, on the lecture content that I posted at the beginning of the week, there was a particular concept that some folks were challenging or struggling with. And it's this shift from vectors to scalars that kind of hurts everybody's minds. Because now we've been doing vectors for so long, like getting yourself to go back into the scalar world is a bit frightening. And so remember, with our vectors, we'd be like, if I wanted the electric field at this point, then we'd look at where the fields are coming from, everything. That's what we were doing on the exam. But because I'm dealing with scalars, I'm just going to be looking at the interaction of each of these things. Or if I want to pick a point again, it would be like the potential because of this charge at this point, because of this charge at this point, because of this charge at this point. The one that I think is more disconcerting to people is when we do energy. So I do this in terms of energy. If I want to know the entire energy of a system, I need to know how much repulsive and attractive energy there is. So you can think of it as how much push or pull is going on will give me the total energy from whatever configuration I have. And so if we think of it that way, if I call all these distances L, that's not the color I wanted. Then like this distance from here to here, they're like square root of 2L squared. And then I'm just literally adding everybody up. So I can say that my energy, oh no, my chihuahua's deciding now is the good time to try to escape her bed. Okay, we're gonna go charge by charge. 1, 2, 3. I want to know the interaction of all of the charges with each other. And so in this case, I have, let's see, Q1 is negative. And then let's just pick Q2 first. No particular reason. Divided by the distance. Now this is just L. And now I can look at it and say, okay, so what about Q1 with Q3? Well, again, there's a negative Q1 and a positive Q3. So this is going to be a minus. And then Q1 with Q3. And then I need to remember that this thing here is still going to be L, but the square root of 2. I'm not squaring these things anymore. So whatever my hypotenuse is my distance. So let's see, I have 1 to 2, 2 to 3. Now I want to look at 3 to 2. Well, they're both positive charges, so that is a plus. So Q3 to Q2 divided by that distance, L. And in a way you can think of it that if I have like a negative sign, well, what's that demonstrating? Well, that's a positive and a negative in some way. Doesn't matter which order they are. So this is actually like an attractive energy. Okay, she didn't fall and break or anything. We're done. And then this one is positive. So that could be a negative and a negative or a positive and a positive. So this would be like repulsive energy. So I'm going to have some amount of pushing away and some amount of pulling in. And we're just adding up those amounts together. I mean, you can kind of think of it as like a scalar force, that thing that we like jumped up and down and tried to get you never to do. So you didn't add up vectors, like a resultant vector together with another vector. Because when they're vector quantities, we can't do that. We have to get them into our XY. A scalar force, and I'm just saying force because force times a distance is an energy or work, right? So scalar force is just saying whatever that force is times that distance. The other thing you can think of that is in terms of work. What we did in my derivation on the videos is I did this in terms of my electric field. This dot product right here, that dot product takes this vector and this vector and turns them into a scalar. That's why everything is a scalar. So we're still looking at something that was a vector, but once I dot them together, they are now just scalar quantities, and that's what we're doing here. Does that help at all with some of the confusion that came up with potentials and potential energy? Or maybe I should rephrase that question. Any questions on that? None? All right. I'm going to erase this and move on to something new. Let's go to our worksheet. All right, so as I mentioned in the videos that Reginald didn't watch, we have this concept of capacitance. I'll say that because we all know it's more than Reginald, but that's okay. I forgive you. And
I'm glad it's not all only on me.
It isn't. It isn't. You're just the one that confessed to it right up front. So I talked about capacitance in there. So I'm going to kind of go back and bring in a little bit of what I explained before, just so everybody's not completely lost as we move on. But I said, remember I did like plates of charge and we looked at electric fields. And I said, okay, so if I have a certain amount of charge here, then I'm going to have like a balance on the other side. And one way to think about that is in terms of our electric fields, I have an electric field coming out of a positive into a negative. And then I also talked about the fact that between these two plates, the electric field is constant. In real life, we get this little bit of bend out on the edges. But we don't need to worry about that right now, because what we're going to work with is going to have these nice, tidy capacitors, because that's what we're making with this. Is we take these two plates, we essentially make a sandwich of it, something like this, and we just keep rolling it up. And so it's going to be something that is conductive. So I'll have like an attraction and a repulsion going, I'm sorry, an attraction between the two. And what's happening here is I get this buildup of charge. I'm going to turn on a battery. Let's put this in a circuit. I turn on a battery, and most of us have done this at some point in time. We have the little batteries and you touch your tongue to it and you feel that tingle. Well, you're completing a circuit. And what you're doing is you're letting charge come out of the end of one end. And if there's a capacitor there, then what that charge does is it spreads out as best it can. And what do you think could happen here? Like if we didn't even talk about the second plate, if I have something charged and I bring it next to something neutral, what's going to happen?
Polarization.
Yeah. So the electrons are going to flee on the other end. And I'm going to have this like net buildup. Of course. Delivery person is here, so bear with me. Rico, come here. I know, I hear too. No. Okay. Give me 2 seconds, folks. I'm sorry. This isn't going to stop until